BKW Physics. I'm Mr. Conley. And we're going to do a projectile example here, another case B example as I call them, where projectile is being fired at an angle. This angle happens to be 53 degrees, and it's traveling at 18 meters per second. The number I gave you this time, the speed, does that represent the vertical, the horizontal velocity, or the radar gun velocity? This is like radar gun velocity. This is how fast it's really going through space, which isn't very useful to us, because when we go to solve this problem, like I need the time of flight, what do I do to find the time of flight? What's my equation for that? Well, all based on acceleration and change in velocity over time. What it looks like for this chapter is time is your change in vertical velocity over gravity. That's this reference table equation slightly tweaked by making that a VV, making this a G, and then rearrange it. Fine, that's not too bad. But what's our VV?
We don't know.
And we got to back up to the picture. So, we're going to make this into a right triangle. Learning from previous knowledge or connecting it to previous knowledge, this is like finding the components of a result. So, let's find the components. The one that's along the bottom we would call X, or horizontal velocity. The one up and down we would call Y, or vertical velocity. So right now we need that one, so let's focus on that one. So what triangle law, right triangle law, is going to give us that? Well, it's opposite over hypotenuse, which is sine. So we got sine of theta equals opposite over hypotenuse. Sine of 53 degrees is the one I'm looking for, over 18 meters per second. Bottom line, the vertical velocity is, let's see if I agree. Yes, I agree. 14.4 meters per second. The whole reason I was finding this was, I needed it over here. Now let's back up to the logic. What? This is a change in vertical velocity, so why do I just put the 14.4 in there?
Well, you just zero VI.
Because what I have right here, this is the vertical velocity initial. It is the VI in the vertical direction. Well then what's the VF in the vertical direction? And the answer is 0, but a lot of you are like, wow.
It won't say it's around, it's
Not even there.
when it hits the top.
When it hits the peak, the high point, at the high point, your vertical velocity is 0 because you're not going up or down anymore. Remember the logic why we can put it in? Makes sense? So 14.4 meters per second, gravity is 9.81. How do we deal with the negative signs here? Well, the way we deal with the negative signs is gravity is a negative, and the one on the top is final minus initial, and this is the initial, so that actually turns out to be a -2, so the two negatives cancel each other out, and you find that the time is, what'd you say? 5.
This is final minus initial.
Yeah, this is change in velocity would be v final minus v initial, and this one's a 0, and this is the 14.4, so it ends up making that the negative, okay? Which is good, because then your negatives cancel out, because you know the time's got to be positive. So that kind of makes sense. Go to max height. What's our equation, Amelia, that's going to work for max height?
Getting there.
Getting there? Hint?
Yes, please. dv equals 1/2 gt squared.
Yeah, but I want to add in the first part too.
So
Because I want to add in the fact that because now we do have an initial vertical velocity, and then the stuff you said, the 1/2 squared. So let's throw this stuff in. All right, so initial vertical velocity 14.4 meters per second. The time of flight, careful here. Are we using the half time?
3.
Full time? What are we using?
double time.
Are we?
Yeah.
When does the max flight happen?
No, it happens halfway. So
So we do use the 1.5. These are the little areas that you can get tripped up on these problems, like plugging in the half time when you meant to plug in the full time and stuff like that. Plus half, negative 9. Make sure that this negative remains a negative because you got to take the positive stuff and subtract the rest from it. Anyhow, how high does this thing go? I ended up getting 10.6-ish. So this will fly to a maximum height of 10.6. And remember also, just to remind you, this is in your reference table. The only thing is, it does not have the V there, it does not have the V there. But otherwise, it appears just as you see it.
It's an A.
Yeah, and this is an A, right? Yeah. That's the way it appears in the reference. All right, and then the range. How far does this thing go? Well, that's a horizontal thing. And we know that the horizontal velocity stays the same, so we don't have to worry about any of the gravity equation. So we can use our old-fashioned distance over time equation, our very first equation of the year. If we rearrange it, we get d equals v times t. And I put the little h just to remind myself that we're talking just horizontal here. So that's where that equation comes from. And, we don't have horizontal velocity. Back to the original picture. We need this. We're going to do adjacent over hypotenuse, which is cosine. So cosine of theta is adjacent over hypotenuse. Cosine of 53 degrees is the one I'm looking for, the pH, over the 18 meters per second. So, how fast is this thing traveling in the horizontal direction?
10.8.
I didn't see it where I did it. Yeah, 10.8. There you go. Good job. 10.8 meters per second. I needed that over here. Now what time do I put in?
Double.
Why 3?
Because the range is the whole part from the start.
I want the whole flight, how long the thing is in the air for. And 10 times 3 is about somewhere around 30, I think it comes out 31.7. And this is meters. So we have found how long it was in the air for, how high it went. Do you agree with that? Good call. Oh, I know why. I see what I did. Back up to the time, I didn't use quite 1.5, 1.4 or something.
Yeah.
Which then kind of has that net effect and slightly changes things in the end. So if we really are just using 3 instead of the 2.9 whatever I got, this changes up to 32 what? So for today, another case B problem, physics.